talk about the gamma ray burst hosted by oxygen-rich galaxies.
Hello everyone. I'm Tetsuya coming from National Tsinghua University in Taiwan. So thank you very much for giving me this opportunity to talk about a little bit of specific theme and also a very low-Z galaxy. So thank you very much. I really appreciate for organizers to give me this chance. Okay, my talk is based on the paper published last year. So in correlation with these guys. Okay, so my talk is about mechanistic measurement of gamma ray burst host galaxies. If I summarize my talk into one sentence, it is something like this. This is also specific, but please don't trust oxygen abundance as an indicator of iron abundance. Okay, that's it. That's my message from my talk. Okay, let's start. My outline of my talk is something like this. I'd like to start from introduction, and then I move on the sample selection and observation by spiral telescope, and then I will show the results, and then I switch to summary. Then in my talk, frequently I use this blanket, for example, FE over H bracket. So please remind that this means that relative abundance. Relative abundance value relative to the solar value. So for example, FE over H bracket equal -1, that corresponds to 10% of solar abundance, solar iron abundance. Okay, let's go. So let me talk about the gamma ray burst first. I'm basically talking about the long gamma ray burst. There are two populations of gamma ray burst, you know. So long gamma ray burst is defined by the duration longer than 2 seconds in observed frame. Anyway, this is kind of brightest explosion in the universe in gamma ray. So at the beginning, we found that bright explosion here, gamma ray part. After that, usually we found afterglow part in various wide range of observed wavelength ranges. So this is kind of bright explosion. Is gamma ray burst. Then why gamma ray burst? So because gamma ray burst could be very useful to trace cosmic star formation rate density. This is star formation rate density in the universe as a function of redshift. So do you know? So people usually try to detect directly detect galaxies in order to estimate the star formation rate history in the universe, right? But gamma ray burst also can be a good indicator of this star forming activity in the universe, because by accounting the number event rate of gamma ray burst, we can convert it into the star formation rate indicator. Then they have three advantages. So gamma ray burst can reach to the very high Z up to, for example, say resolution 10 or something can be detected. Then gamma ray part. So it's because it's gamma ray, so gamma ray can penetrate the dust. So this is strong against to the dust extinction. You can trace the dust obscured star formation rate from gamma ray burst. This is advantage. Also, even though we don't detect actual host galaxy, even though we don't detect host galaxy of gamma ray burst, still we can count the star forming activity from the count rate of gamma ray path. So this is kind of big advantage of gamma ray burst when we use this as a tool to trace star formation rate history. But of course, in order to take advantages of these three, it's very important to understand what is host galaxy. So what kind of star formation is traced by gamma ray burst. So we need to understand these things. So my talk is about these things. So we want to understand what is host galaxy, physical property of host galaxy of gamma ray burst. This is key. So this is kind of imaginary picture of gamma ray burst. So you know, gamma ray burst is long gamma ray burst is believed to be related to death of massive star, which is fast rotating. So this fast rotation is very important to launch a relativistic jet. So and then if we observe this jet if we observe this massive star along this jet axis, we can recognize this massive star, this explosion of this massive star as a gamma ray burst. So this is kind of theoretical view. In terms of theory, so iron abundance, Fe over H, is a key parameter. Because in theory, so very low iron abundance, which is less than 10% of solar value, is required for massive star to become gamma ray burst. Because this iron drives a strong stellar wind. Then this strong wind takes a rotational moment take away. And then in the end, if we have an amount of iron, so this lose rotation, and then this massive star cannot become GRB if the metallicity iron abundance is high. In other words, we need a low metallicity to have a gamma ray. This is important thing from theoretical view. But in observation, okay, so people usually use oxygen abundance, so you know. People usually use O over H, oxygen abundance, as an indicator of iron abundance of gamma ray burst host galaxy. Because, so as you know, so this is a typical spectrum of host galaxy of gamma ray burst. And then, as you can see, a strong emission line come from oxygen element. So that's why people use oxygen abundance as an indicator of iron. So then there is a big mystery in gamma ray burst people. So somehow, some gamma ray bursts are hosted by galaxies with high oxygen abundance, which is comparable to solar value. So this is mystery because this value is, roughly speaking, one order of magnitude higher than theoretical limitation. This is mystery. Then this is mystery, but of course, so it is not necessary for oxygen abundance to be exactly same as iron abundance, you know, because these two are different things. So in theoretical view, iron abundance is very important, but observationally, oxygen abundance usually is. Then point in my talk is that, okay, we need to measure directly iron abundance of GRB host galaxy to understand how the gamma ray burst host galaxy is special or something like that. Then, but there is a still problem because iron emission line from iron element is basically very weak, so that's why people usually don't think about it. But in this case, in my talk, in order to overcome this problem, we use a small telescope. So you know, small is very big telescopes. Then small enable us to measure the iron abundance, especially for low latency galaxy. Sorry, for this is low latency. But anyway. So as trial study, so we selected two host galaxies here, two local host galaxies of gamma ray burst. One is a host galaxy at radius 0.089. Then actually this is a host galaxy. Left circle is location of gamma ray burst. Anyway, so this host galaxy curiously show the oxygen abundance close to solar value, which is one of the magnitude higher than theoretical prediction. Theoretical limitation. Then also another one is, this is also nearby host galaxy, and then, so this is the host galaxy, and then, so we extracted two spectrum in this case, because this is spatially resolved data, and then we can extract the spectrum at the position of gamma ray burst here. This is one spectrum from the position. And also we extracted the spectrum from the most brightest region, which is a Wolf-Rayet region. So actually in this case, Wolf-Rayet region is lived away, offset from the actual location of gamma ray burst. Anyway, so we extracted two spectrum at gamma ray burst site and the Wolf-Rayet region, which is brightest region for this host galaxy. Then this is example of observed host spectrum. And then black solid line is observed spectrum here, and then red line is stellar component fitting. So in order to extract pure emission line component, so we need to extract the absorption line features coming from a stellar component. So we fit, this is model fitting plotted by red line. Then subtracting this red component from the observed black, and then we got pure emission line component. Shown by green line here. So as you can see, for example, previously we used this kind of very strong emission line to estimate oxygen abundance. So in this case, okay, we use this emission line here. So we successfully detected emission line, very weak emission line from iron elements. And then, okay, I skip everything to calculate the iron abundance, but so you can imagine, if we detect this emission line, we can calculate the iron abundance for this host galaxy. So actually, this is a little bit complicated things in between here, but I don't have time to say, so let's skip. Okay, this is another host example. We extracted two spectrum from this host galaxy. One is Wolf Rayet, that is brightest region. Actually, in this region, we successfully detected iron emission right here. At the position of gamma ray burst, we couldn't detect any clear picture of iron emission line. So that already suggests the lower abundance of iron. Anyway, so we can calculate the upper limit of iron abundance from the upper limit plus upper limit from here. So before going to talk about gamma ray metallicity iron abundance, so we need to compare gamma ray burst of the galaxy with normal star-forming galaxies, if possible. So in principle, I want to compare with gamma ray burst of the galaxy and normal star-forming galaxy, but it is not easy because we are now comparing the iron abundance. So it is still very difficult for normal galaxies to measure the iron abundance. So this is oxygen abundance as a function of stellar mass, so-called mass metallicity relation. So normal galaxy distribute from Sloan digital sky survey distribute something like this, mass metallicity relation. But not all of them. We cannot iron abundance for all of them. Then what we can do is just select iron abundance measures some galaxies from Sloan digital sky survey, which are plotted by black dot here. Then I don't think these guys are normal galaxies in the universe because, as you can see, this population already biased towards low metallicity. So, but no way to compare anyway. So we use these guys as a comparison sample. But please keep in mind that our comparison sample is already biased towards low metallicity. Okay, let's compare with gamma ray burst of the galaxy. This is main result of my talk. So this is actually first time to compare the total iron abundance as a function of total oxygen abundance for gamma ray burst, as well as in comparison with star-forming galaxies. So total means that we calculated iron element not only in gas phase but also dust phase. So iron is known to be locked in, many of iron is known to be locked into dust. So we corrected this factor in order to calculate the total iron abundance, including both in gas phase and dust phase. Okay. Then dashed line here corresponds to solar value. Something like this, 4.0 is solar value here. So actually, let's see the comparison sample here. Black dots is actually biased to a low metallicity, which is lower than solar value, right? Actually. Then, so these current data points are from gamma ray burst of the galaxy. So at the site of gamma ray burst, we just could calculate upper limit of iron abundance. So actually, so this is just the upper limit, but this is not conflict with theoretical prediction plotted by this blue area. This is theoretical prediction. This is only our upper limit. So there is no strong conflict between these two. And also for these two, this host galaxy actually shows higher oxygen abundance curiously, so which is almost comparable to solar value. Actually, oxygen abundance is very high, but the iron abundance is basically consistent with theoretical prediction within the error bar. So that means, so even though this was a mystery because curiously some of gamma ray burst the galaxy shows high solar abundance. But actually, if we check the iron abundance, this is basically very low, even lower than this comparison sample, which is biased toward lower metallicity. Anyway, so point is that regardless of oxygen abundance, so gamma ray bursts of the galaxy showed low iron abundance. In other words, so O over Fe, in terms of O over Fe ratio, this ratio is probably very high for gamma ray bursts of the galaxy. This is kind of special. Actually, the gamma ray bursts of the galaxy showed one of the highest value of the comparison sample. Then, if we assume this O over Fe for other host galaxies, GRB host galaxies, which is, for example, highest oxygen abundance, so then we got this value. Fe over H is some around the -1 or something. This is basically consistent with theoretical prediction. So that means probably gamma ray burst of the galaxy is kind of special type of galaxy, at least at the local universe. And then that's why even though we have a high oxygen abundance, the iron is very low. So this is kind of, okay, this is final. This is kind of expectation because gamma ray burst of the galaxies is known to be a young population, young summing galaxies. Young means they don't have enough time to produce iron abundance from type 1a supernova because type 1a takes a long time, for example, 1 giga-year time scale. If the galaxy is younger than this time scale, so there is no time to create iron. So these things enhance this oxygen over Fe ratio as seen in gamma ray bursts of the galaxy. So that this is kind of physical interpretation of this high O over Fe value. Okay, I stop here. Thank you very much.
Yeah, Hashimoto-san, can I assume this is a very high oxygen to iron ratio? Is the average value of the galaxy or just local value?
I cannot assume it is average because probably gamma ray burst host galaxy is very special type. Then this is probably, this is my guess, probably one of the highest value. So among the surrounding galaxies in the universe. Then because this galaxy is already biased sample, but the host galaxy shows still maybe comparable to or higher than this biased one, then that means maybe this is.
Yeah, but I mean here, this value is an average for this single galaxy. I think it could be just coming from locally here, and not the average value. Then yeah, so this is very important to compare it with the chemical evolution speed.
Yes, thank you very much. Yeah, it's actually critical point. So I expected some some result from spatially resolved data, but this is very important to answer some question. But current observation it's a little bit difficult. So even though in local universe, so yeah, maybe TMD or something like that can do it in the future.
I think when you show the spectra, you subtract the stellar continuum by fitting the SSD the model. I think for this particular stellar template, they assume solar abundance ratio abundance pattern, which is O by 3 equals 0. So, but yeah, you're doing the gas but there is some inconsistency.
Could be, but main purpose to subtract this stellar component is estimate correctly the emission line around this here.
But here, if we use this absorption feature to get the ion abundance for stellar component.
For stellar component,
there is an emission, but there is absorption as well for ion absorption there.
Actually, there is no clear feature.
Yeah, not clear.